Hello, this is Mr. Dobson, and today we're going to be looking at the first unit from the AQA Physics course, Matter and Radiation, and we're going to focus on the atom and radioactive decay. Now, in essence, this is a review of stuff you should remember from GCSE, but it takes it a little step further in a couple of places. So first of all, we're going to be working on atomic physics, so we need to understand the atom, and we need to come in with the right understanding from GCSE. So at GCSE, we'll tend to look at the Rutherford model of the atom, which is here. So this is the Rutherford model. Okay, I've picked a helium atom because it's the smallest atom that actually has protons and neutrons in it, and in sort of normal isotopes. So it's a good one to start off with. It has all the parts that we need to look at. So Rutherford did his famous experiment where he fired little particles at a gold leaf, particles of radiation, and he worked out there was this dense centre because some bounced back. So if you remember, we're not going to go into detail on that because that comes up later in the course, but he managed to develop this idea. So we have this really dense centre here called a nucleus, and we have the orbiting electrons around the outside. Now, a lot of the time we drew the electrons in rings on the page, but we was probably all aware to some degree that they're actually three-dimensional, which is this picture here tries to show as a shell. So a three-dimensional shell around the nucleus. It's very difficult to see it in 2 dimensions on a screen like this, but it's not a bad way of showing it. What isn't in a great proportion here is the size of these particles, the electrons. In actuality, these are much, much, much smaller and very, very far away. The atom itself is 99.9% empty space. So it's mostly that bit in between. But looking at that bit in the middle, we have, in this case, 2 protons and 2 neutrons. Okay? What do we know about these things? Well, we would have learnt certain things from GCSEs. The first thing we'd learn is charge. So we can see that we have a positive charge on the proton and negative charge on the electron. And no charge on the neutron. Now, the plus and minus, what do they mean? Well, some of you may or may not remember what charge is measured in. Charge is measured in coulombs. Now, what is the chances that they happen to have exactly a certain amount of coulombs? Well, you might argue it depends. If the coulomb was discovered and they used this as a value to measure it by, maybe. But it's unlikely otherwise that they have +1 or +2 or +3. But we do actually count them as +1 and -1. Obviously, the 0 doesn't have a number. So when we talk about that 1 and the -1, we're actually talking about multiples of something specific, because the real number for the charge and the electron is, if we zoom into a section I've taken here from the sheet that you get in the exams, you'll see, if I can draw around it, the magnitude of the charge on of an electron, which is given the symbol little e, and it's 1.6 times 10 to the minus 19 coulombs, a number that you'll end up being very familiar with. So we can see it isn't an exact number. The charge on E isn't the exact number, it's there, but what we do is we talk about it in multiples of this number. Then we can just talk about plus and -1. Much easier. If we then want to know the actual amount in coulombs, we can later on multiply in this number and get the actual amount in coulombs. But for most of the time, we're looking for cancelling out, etc. A lot of the time we don't really care about the actual number. We're looking at how many multiples of it we've got. You'll notice nowhere on here does it say the magnitude of charge on a proton. Well, that's because it's the same as an electron. So they chose to use the electron as the one we use. Obviously, the only difference is the same in magnitude. You notice that it did say magnitude there, but it's opposite in polarity. So the magnitude is 1 times 10 to the minus 6, 1.6 times 10 to the minus 19. The magnitude of this one is 1.6 times 10 to the minus 19 coulombs. But this is plus and this is minus. Okay, neutron obviously has 0. So that's important. So we know that these are negatively charged, these are positively charged. Now there are several problems with this model that I don't know if you've ever really thought about before, and it comes down to our understanding of what happens when we get different charges interacting with each other. So if I was to place a positive charge and a positive charge, if my pen works, next to each other, what would happen? Well, we should hopefully remember that they would repel each other, they would move away. If I was to get a negative and a negative, we have the same effect. Because they're the same charge, they repel. There we go. But, hopefully remember that if they're different charges, and that could be either way round, so we often write it that way, then they will actually attract each other. So they're going to move towards each other. So opposites repel, up here, and opposites attract, and the same repel. Now looking at our picture of the atom, if you understand this concept, you can see two problems. The first one, the nucleus shouldn't exist. We have two positively charged particles in the middle here, and they should want to repel each other, and you should want to tear the nucleus apart. And we also have two other problems, is that we have we have electrons here that are kept at a distance from the centre. Of course, we know that this electron is going to want to move itself towards that positive charge in the middle, and therefore the electron should spiral in and the nucleus should explode apart. Two things that don't happen. We know it don't happen because we're here. If it did happen, then we wouldn't be here to have this argument. So clearly there's something more going on here than meets the eye. So what we're going to try and do is we're going to address some of them issues. We're going to look at why the nucleus stays together here in this video. Later on in the video about quantum physics, we will understand why the electron doesn't spiral in. So first of all, we need to make sure that we know how to write and talk about these things in our work, because we're going to be doing maths with it. We're going to be showing people that we understand how to use it. There's some words we need to make sure we know, so we're going to look at the first key word here, nucleon, which is a new word that's introduced at A-level. And it simply means any particle that's inside the nucleus, so be it proton or neutron. So protons and neutrons are both nucleons. Okay, it's just a simple word. Rather than having to say protons and neutrons every time, it just makes it easier to say nucleon. And the word really does kind of hint at what it is, because it comes from the word nucleus clearly. We're going to build up our idea of the atom to this nucleus full of nucleons and the odd electrons running outside. We already said that really we should see it in shells. The real version of what the atom looks like actually looks something like this. Now, over the course, parts of this will become clearer to us and will be explained. Other parts, not necessarily, okay? But this is a much more quantum physics interpretation of what happens in a nucleus, or in this case a helium atom. Okay, so we need to be able to talk about this atom and the components inside it, the nucleus and the electrons, without having to draw it every time, because that would get very, very tedious. So we've come up with a way of writing. Okay, so this is our way of writing. We use isotope symbols, and we draw it as an element. In this case we write X, but because we don't know it. But we'll write it out for helium, the one we've been looking at. So helium, our symbol is He, capital H, small e. Then we look at the mass number. Now the mass number is the number of protons plus the number of neutrons. Or we can now say, from our new word we know, the number of nucleons. And that's why atomic mass is also sometimes referred to as nucleon number. So the nucleons, in this case, well, we have 4. our 2 protons and our 2, so make that 4 visible, 2 protons and our 2 neutrons in the nucleus. Then we look at the atomic number. The atomic number is number of protons. It's also sometimes called the proton number because, again, it is the same thing. This is the proper term for it. This is the way we would normally talk about it to some degree. So I have 2 protons in my helium nucleus. So if I just add that in now, and the pen doesn't want to work today, there we go. 2 protons. And that's how I would write this element that we see at the top here for helium. Now, that doesn't reflect its charge. So we've got charge to deal with, but it does tell us everything about the makeup of the atom. So I can have, for instance, another version of helium. So I could have another version of helium. Now, it must still have 2 protons because the proton number determines what element it is. If we had 3 protons, we'd have lithium. If we had 1 proton, we'd have hydrogen. So that number can't change without helium changing. But the top number can. I could have helium 5-2. That would indicate 5 nucleons, 2 of them being protons. That would indicate to me that there must be 3 neutrons here. So the difference between this one and this one is 1 extra neutron. So that would be, if I was to go back to my picture above, adding an extra neutron. And now I'd have helium 5, as we would call it. Sometimes these elements appear in nature, sometimes they don't. The one on the periodic table is the one that's most, it's like the average value, the one that's most abundant in nature. But there are many more that aren't on the periodic table. You should hopefully remember from GCSE, the word we use to describe 2 elements have the same number of protons but different number of neutrons as isotopes. Okay, isotopes. Very important, and the exams often have the question, describe an isotope, or what is meant by the term isotope. And they're looking for that 2-part answer. Same number of protons, different number of neutrons. Now, this isotope notation, or this way of drawing it out like this, really is only directly telling us about the structure of the nucleus. So here it tells me, how many nucleons I have, how many of them are protons. It's really only referring to the structure of the nucleus. And we often therefore use the word nuclide here. I think nuclide, I think is the way I pronounce it. We use the term nuclide to describe these different configurations of nucleuses. So this is one nuclide of helium. This is another nuclide of helium. Here's a nuclide of hydrogen, etc., etc. So the word nuclide represents the different configurations of nucleus that we can assemble, all the different periodic table plus all its isotopes, all different nuclides. Now lastly, we did mention this does not tell us anything about charge. So in essence, it's only talking to us, well, let's say some stuff about charge, because charge is supplied by protons, but we know the total charge of an atom is partly to do with its protons, but partly to do with its electrons, and there's no direct information here about electrons, because it's about the nucleus. But we can infer, if no charge value is quoted, then it must be a neutral atom. In essence, when you see nothing written on the right hand corner, it's kind of saying 0 charge. In which case, these 2 that I've drawn here and here must both have 2 electrons, so that they cancel out, their negatives cancel out the positives, so they cancel out the 2 protons here. Now I can have charged particles, which I didn't add to my keywords, but you should remember a charged particle is called an ion. So if I was to have helium 4-2 like this, I can have it plus. Now that would mean it's got a charge of +1 overall. How do you get a charge of +1? Well, the positive is supplied by protons. We can't change the amount of protons, so there must be 2 protons So to leave it positive at the end, I must not have been able to get rid of or cancel out all them protons, which means I must have one less electron. So it's kind of weird, because obvious to some degree, if we were to draw helium 42 minus, well, extra minus must have an extra electron. Easy. But when it's positive, it isn't a case of it has an extra proton, because we've talked before, we can't change that number, can't affect the nucleus in that way either. So this must come from having one less electron. So if you were to remove an electron, then you'd have a positively charged atom. If I was to add an extra electron on, well, I couldn't add it on this first ring, I'd have to go to the next one, we could make it minus. We can actually have a doubly ionised +2 or -2 as well, which would be a doubly ionised helium atom is very important to us, and we're going to look at why in a second. So there's lots of different ways that we can write about atoms in this isotope notation. We can learn about all the nucleide information, all the stuff that's going on in the nucleus. We can also infer charge information, knowing about what's going on in the shells around it. We can't know exactly where the electrons are in the shells, but we'll look at that later on in another part of the course. But that is where we should know from GCSE. And we do sometimes, I did put this at the bottom here to look at briefly, we do sometimes know names for these different isotopes. So for instance, a hydrogen, we've got protium, which is the standard isotope of hydrogen. You've got deuterium, which is heavy hydrogen, because it's got an extra neutron. And you've got tritium here, which has got 2 neutrons and 1 proton, so 3 in the nucleus. So they actually have names, but for a lot of things they don't actually have names. We haven't bothered to name all of them, there are so many. So what we end up with is, we would call this helium 5, we would call this helium 4. So that's always the way you can talk about it, and that's okay. If you happen to know a name for it, that's normally okay too. I wouldn't ever recommend using that in an exam though, because just in case you got confused by the name, it's just unnecessary element of confusion where you could make a mistake. The next thing we're going to look at is how we can use this isotope notation to actually write down the individual elements of the atom itself, the particles that make it up. And you should remember this to some degree from when you've done alpha, beta and gamma radiation before, which is what we're going to come on to next. So alpha particle, well, it's a part of a nucleus. It's 2 protons and 2 neutrons. Well, when we look up here, we see 2 protons and 2 neutrons, especially if I go back and rub out my extra one I added. We can see 2 protons and 2 neutrons is actually the nucleus of a helium atom. So at GCSE, if we're talking about alpha, we would tend to write the symbol alpha, but at A-level, well, we don't need to use the symbol alpha. Instead, we can actually write what it is. We can write He42. Now, it's the nucleus of a helium atom. It's not the helium atom itself. It's not giving off helium. If it was giving off helium, no one would get killed from alpha radiation, and we'd all just get squeaky voices, I guess. So, how do we represent the nucleus of a helium atom? Well, the nucleus is the bit without the electrons. And what would happen if I took the electrons away from the helium atom? Well, there were 2 electrons. That would mean that we'd remove 2 electrons. You'd have a charge of +2. So I could actually write the charge information in here, and now I have a helium nucleus. So that is actually how you can use that notation to write alpha. So we have a helium nucleus, 4,2, doubly ionised, so it's just a nucleus, the electrons are missing. Of course, that is why it's so strongly ionised, and of course it's desperate to try and find these electrons out in the world and become stable helium. So, moving swiftly on, if we go to beta decay, well, beta decay we would have remembered from GCSE, we'd write like this, but we should remember hopefully that it's a high energy electron. Well, how do we write an electron? Not overly easy, but we can give it this letter E. It's the standard letter for electrons, that's fine. But how do we put its numbers? Well, what's its atomic mass? Well, if we look over here, a reason I brought this table in, it's got some representative of mass here in atomic mass units. That means in multiples of the mass of a proton. So we see here, because a proton and neutron have almost exactly the same mass, which we'll look at in more detail later, we can say there's 4 nucleons and then 4 times the however much one nucleon weighs, or the mass, sorry, of one nucleon. So we see here is a very large mass. We get to the beta particle, 1,837th of the mass of a proton or a neutron. Very, very, very tiny. So small, in fact, that if we do calculations and we involve it, it will disappear in our decimal places, and we'll look at that when we do specific charge. So, for all intents and purposes, it has no mass. In this nucleon, this isotope notation, we're only talking about the mass of the really heavy stuff in the middle. So, in that sense, it has none. Now, how do we put the number of protons? Well, you can't put number of protons because there are no protons. So how do we deal with that? Well, we go back to the other way of dealing with the number at the bottom, which is dealing with it as the charge of the nucleus, and then we fudge it slightly, really, because technically it should be the number of protons, but if we deal with it as charge, well, electron does have charge, so we can make an assumption there. So if the proton would give us a +1 in the bottom left-hand corner, the electron must give us a -1. And now we have something that we can use to write beta radiation in isotope format. Now lastly, gamma. Gamma is a bit different. Gamma is a light ray, so there's not much we can do for that. So tend to just write it, as you can see on the left, as gamma 00. It doesn't actually have any mass, it has no charge, so we can't rename it something else because it's not really something else, it's just a ray of light. All these things hopefully you remember from GCSE. Okay, lastly, before we move on to the radioactive decay equations, we've got a new bit that you've never seen from GCSE. Like I said, there's always a little new bit. In this case, it's called specific charge. So specific charge, the word specific in physics means per unit mass. Now we're going to deal with a lot of things, especially in the second year, where we'll start to look in the sense of per unit mass. What that means is it's a way of comparing things of different masses against each other, where we don't actually have to worry about the fact that one's got more mass than the other. For instance, if I was to look at the density of a football compared to a golf ball, if I was just to weigh them, I would see that the golf ball is much lighter than the football, but we know the golf ball is actually far more dense. So what we need is a way to compare them that looks at how much mass per centimetre square, so in each bit. That way we've got a more direct way of comparing. This is the kind of thing here. So specific charge is a direct way of comparing the charge by not worrying about the mass. And we do that by not worrying about it by dividing the mass out of it. So what we can then compare specific charge to specific charge. Now, what you really care about for the exam is that if you get a question of its specific charge, you do charge divided by mass. But the reason for it is because it's a per unit mass calculation. You'll find they are quite useful from time to time. How do we do it? Well, simple. We take the charge and we divide by the mass. But the simple bit is the equation. The difficult bit is knowing what numbers to put in here and here. It's not overly difficult. The problems arise when we don't read the question correctly. So we need to know if it says the specific charge of helium, for instance. So the specific charge of helium, if I was to type it in at the top here, there's no charge to helium. I mean, if it didn't tell us it's an ion of helium, then there's no charge, and therefore it has no specific charge. But if they were to tell me it's an helium ion, +1 or -1, for instance, then there would be a charge. So in that case, if I was to write this out, get a new colour, it's working. if I was to write this out, we would say that the specific charge, and this is for, let's say, helium plus, so helium plus 1. Okay, the specific charge, well, how much charge have I got? Only plus 1, so I'd have 1, and now I need to write this in actual coulombs, so I've got to times it by E, 1.6 times 10 to the minus 19, divided by, now I've got to look at the mass. Well, in this I'm going to have 4 nucleons, each nucleon having roughly the same mass, so 4 times, and if we go over to this sheet here, we'll find the rest mass of a proton and a neutron here, electron there, but we're going to come back to why we don't care about that. You'll notice they are the same to 2 decimal places. So providing we don't go to beyond 2 decimal places, we don't need to worry about the 3 or the 5 here and here. We can just use 1.67 times 10 to the minus 27. So that's much easier. So 1.67 times 10 to minus 27. That's a 7. There we go. And that's how we would work out the specific charge of a helium atom that's singly positively ionised. Now you might question, why have I not added the mass of the electron? There's still 1 electron in there. If it's only plus 1, there must still be an electron in there cancelling out the other proton. Well, because the electron's mass is so small, it's times 10 to the minus 31, if we can see on here. It's far beyond the decimal places that we've gone to. So if we could imagine this is to the 27, this would be to the 28, 29, 30, 31. The 9 is going to be here somewhere, beyond the decimal place that we've already ignored, just to use 1.67. So any calculation, even if I have 100 electrons in there, well, by the time I'm getting up to the point where I've got 100 electrons, I'm going to have 100 protons. So again, it's still not going to amount. It's still not going to matter. So we don't need to worry about the electrons in the mass. We do need to worry about them in the charge because they're charged, but not in the mass. Now you put that through the calculator, you get an answer. The next way we could come up is that they say, well, okay, well, not an ion of helium, a helium nucleus. Well, of course, a helium nucleus we've already seen is equivalent of plus 2. So that's fine. You do it exactly the same way, but you would have on the top, you'd have 2 times. Underneath, you'd still have 4 times. It could be they'd ask you for the specific charge of a proton. Okay, that's possible. So a proton would have 1 times on the top and 1 times on the bottom. Now, they could ask for a specific charge of a neutron. Well, that would be 0 times on the top, so that ain't going to work. They could ask us for the specific charge of electron. Now they do. Now this is when the charge of electron will matter. So that would be 1 times E on the top and 1 times the mass of an electron on the bottom. And that's the one time we would care about the E, because there's no protons or neutrons around to dwarf it. A little hint, when you're doing calculations on specific charge, the electron has the greatest specific charge because it has the same charge as a proton, but much smaller mass dividing by it, so we'll end up with a bigger number. Likewise, neutrons add mass without adding charge. So the more neutrons there are in an atom's nucleus, the smaller the specific charge of the atom. So there are 2 things that can help you make decisions about which atom may have a larger or smaller specific charge without you actually having to do the calculation. I recommend that you do the calculation in the exam, but of course if you're using a time stretch, you should be able to just look at them and make a reasonable assumption as to which one might have the highest or lowest specific charge, the kind of way that it comes up in questions. So lastly, we're going to, as I promised, look at what keeps the nucleus together, even though that it shouldn't be, and then we'll go on to doing some nuclear equations for what happens when it doesn't stay together. So this is what we know about electromagnetism. It's repulsive between 2 of the same charge. And the interesting thing about electromagnetism, if you remember this from when you have played with magnets, because the same force that repels charged particles is the same force that repels magnetic magnets. As you move them further apart, it dwindles significantly. But as you start to bring them together, the force starts getting more and more and more. If you try to bring two North Poles together, eventually when you get really close to each other, it becomes nearly impossible to make them push together. Now, if you were to plot that force required on a graph against distance, this is what we would see. So you can see at long distances, at big separations, I've lost that at the bottom of the screen, sorry. At big separations, this force is very, very small, in this case about 100 newtons. At very small separations, it becomes increasingly high force is required. So that means that as we move two charged things together, the closer they get together, the more they try to push each other apart. Now, of course, we're trying to cram protons into a nucleus. We're going to get them very, very close together. We're going to get them in the femtometer region. So that's kind of important. They should tear each other apart. They should tear the nucleus apart, go whizzing off in either direction just to get away from each other. The only way it's possible to overcome that is by another force. So I'll give you an example. This is the electromagnetic force. It's one of the four fundamental forces in nature. One of the other fundamental forces you would have come across was gravity. So let's say I have a paperclip. Okay, there's my paperclip. And I let go of it. Okay. So I'm going to see if I can select my paperclip, yes, and now hopefully, yeah. So I've got a paperclip and I let go. And assuming we're in a gravitational field, gravity will take over and the paperclip starts falling. Fine. Gravity, very, very strong force, everyone thinks. Actually, it's incredibly weak because I can defeat gravity by adding in a magnet at the top here, and if the metal that the paperclip is made of is a ferrous metal, when they're normally made of mild steel, I'm assuming, because they all normally do move towards a magnet. When I let go, if I hold it sort of here, maybe it will still drop, but once I get it, oh, hold on, got to get it again. Once I get it to about here, if I let go, instead of falling, it's going to go up and stick to the magnet. So we can see when you have two forces interplaying, at certain separations, we might get, so it goes, one thing happens. But if one force is stronger than another force at short distances, then actually when we get to a certain point, the opposite happens. So there must be, or the only way to explain why the protons would go together, is that there must be another force that's stronger than electromagnetism, but only works at a very, very small range, smaller than that of the electromagnetic force does. That would then give us that situation. And because we're physicists, and because we're really rubbish at coming up with names, when they said there must be a force that's stronger than electromagnetism inside a nucleus, they called it the strong nuclear force. So, this is the strong nuclear force. Now, it is a little bit different. The strong nuclear force, and you can see on the diagram we have here, is both repulsive and attractive at different times. So here, this, where's my pointer? This is attraction. So on this half of the diagram, we're talking about it being attractive. On this side, we're talking about it being repulsive. So, if we're about 6 femtometers, we don't even know it's there. The force is incredibly weak at them distances, negligible, it has no effect anymore. But as we start moving closer together, it starts to become attractive. If we go less than 5 femtometers, its maximum it can reach up to about 5 femtometers. If we start going to smaller distances of separation than 5 femtometers, we start moving to a period where the strong nuclear force is attractive and will now pull together. And what does it attract? It attracts the particles inside the nucleus, the protons and the neutrons, are attracted together inside the nucleus by the strong nuclear force. And as we get closer, it actually becomes really strong. So it's going to try and hold them actually about here. So it's going to try and hold them all at about 1.34 on this diagram distance apart. Because, weirdly, if we start trying to go closer than that, rather than this graph carrying on as a smooth curve on the underside that we might expect, weirdly, if we get closer, they start to repel each other. So the strong nuclear force has the reverse effect, pushing them really far apart. And in fact, at less than half a femtometer, it's completely repulsive. So here it's just not as attractive. The attraction's going down. But once you get to about half a femtometer, it actually becomes repulsive. It's going to push them apart. That means that the strong nuclear force will allow two protons to come together, but will never allow them to touch, which is kind of strange. So it brings them together, but never allows them to touch. Now, what we've got to do is put the two things together, like we did over here. We talked about gravity and electromagnetism. We combined them. Here's the graph for electromagnetism. Here's the graph for strong nuclear force. And the graph on the left combines the two, which I really like this graph. It really helps you understand what's going on. So, we take what we're going to imagine here is that I have a proton, here. Okay? And I'm going to draw myself a little proton over here that I should then be able to select, and I should now be able to move. So I've got my little proton, and I'm going to, oh no, I've changed its shape. Let's try and move it. There we go. I'm going to bring him closer. So he starts here at 6 femtometers. There's a repulsion. It's not a huge force of repulsion at this point, but it's there. Probably if we was in a free gravity or whatever, they would just, gravity wouldn't even affect these, but if it was in free space, maybe push them apart, but not much going on. Then we get to here. Now I'm starting to feel the force of repulsion. It would be harder and harder and harder for me to move this proton closer to the proton that I'm moving it towards. There would be a stronger and stronger force. I'd actually have to do work to overcome this force, to push them together. Then all of a sudden I get to here and suddenly, it's not hard to push. In fact, it takes over. It does it itself. So really weirdly, I'm having to push harder and harder and harder and harder and harder and harder, and then suddenly, it goes to there. Now, it can't go any further than that because it starts to be repelled by the strong nuclear force. This is the area where the strongest force is, so it would end up sitting right there. And it's now held there, and that explains how the protons can be held in the nucleus, why they're held in that tight little tiny structure in the centre, why they're not tearing it apart because of electromagnetism, because electromagnetism is not as strong as the strong nuclear force, and therefore that explains the nucleus. That explains why it happens. Now what we need to know for exams is that the strong nuclear force is repulsive at less than half a femtometer, and attractive up to 5 femtometers, which is really important. And we'll look at the exchange particle for the strong nuclear force later. It should be worth mentioning that along with gravity and electromagnetism and the strong nuclear force, there's another force that goes on inside the nucleus, not quite as strong as the strong nuclear force, so being physicists and being rubbish at names, we call it the weak nuclear force. And the weak nuclear force is partly what is responsible for decay. Now the last thing I want to look at in this first video for the first unit is decay. Now the decay ones that we're going to worry about to begin with, mostly the top two here. We're not doing all of these, but I found this diagram that's quite a nice one. So we're going to mainly look at the top one. We need to be able to write decay equations. Now decay equations are pretty good. I don't think they're overly taxing. You should have done them at GCSE. So here we have an element, AZ. So if we take an element that we might likely see in this, which is uranium-238. So uranium-238 92. I can make the little 9. There we go. Uranium-238 92. Now, if that decays via alpha, we're going to lose a helium nucleus. So we're going to end up with something here plus a helium nucleus, which I can write as alpha 42, or I could even write as He. Most of the time in the book, they tend to write alpha in this scenario to begin with, and then we don't really come back to alpha much, really, so we tend to just... Beta's a little bit different, we'll look at that in more detail, but yeah, alpha's fine. Helium, also fine. Now, we've got an element on the left of the helium, so we're going to get the helium out plus the uranium with the helium nucleus missing, the alpha missing. Because the number of some protons have left with the helium, it cannot have the same number of protons anymore. If it can't have the same number of protons, it must be a new element, which is indicated in this diagram here as this is X and this is X prime, indicating a new version. A lot of the time you'll see it written as X and Y. That's also perfectly acceptable. The good thing with primes is you can just use as many as you want. You can go prime. So like you can go in several without it running out of letters. Of course, if we do actually know the element, we could write it in. So I happen to know that when you take 2 protons away and move it to 90 protons, you have thorium. But in a physics exam, you will never be expected to know that. You just write element X. You don't really care. You're not given a periodic table. That's for the chemists. Then I just got to make the maths on the left, the right-hand side, add up to the numbers on the left. So what number? If I look at the top first. So look at the top here first. What number here plus 4 would give me 238? Now clearly that would be 234. If I look at the bottom, what number plus 2 would give me 92? That would be 90. And I can see that after alpha emission, we'd have thorium 234 left over, okay, which will then go on to do its own decays, etc., etc. The general formula is the one that you see at the top here. You'll find it in the books. So we just take the number here, A, and we subtract 4. So 238 minus 4 is 234. We take the number here, Z, which was 92, and take away 2. So 92 take away 2 is 90. I much prefer to look at the other way because then it almost double checks your answer. 934 plus 4 gives me 948. It's correct. And every time you do these, do that double check on yourself, because if you do a string of these, you end up one mistake early on, filters through all the elements below it. Okay, beta decay, same thing. Let's say thorium undergoes beta decay. So let's start with thorium 2, 3, 4, 90. And that's going to undergo beta decay. So we're going to get a new element out. Now in this case I don't actually know the element, so I'm going to use X. So it's mystery element X. Plus I'm going to get my beta out. Now again, the book initially writes it as beta and then moves on to writing it as E. But I'm going to write it as E. And we know that it has no mass and -1 charge from what we did earlier on. Then I've got to make the numbers match up again. So if I look at the top, I've got 2, 3, 4. Something plus 0 gives me 2, 3, 4. Well, that's not difficult maths, is it? 2, 3, 4 plus 0 gives me 2, 3, 4. Something -1 gives me 90. Well, that must be 91 then, isn't it? So now 91 minus 1 would give me 90, and I've double checked my answer like that. We can see that when we do alpha decay, we have the effect of dropping the proton number down 2. But when we do beta decay, we actually have the effect of moving the proton number up 1, which is quite interesting. Now, it doesn't show it on this diagram, but we're going to be a little bit more specific in that we're going to add one more thing, because every time you get an electron out, you actually get another particle that is a new one for you, which is an anti-electron neutrino, which is a kind of curvy V with a little e. We'll look at what the electron neutrino is later, but it has no mass and no charge. The last thing we might choose to look at would be gamma emission, but gamma emission is just a pure emission of energy. It's much less specific. It can happen through several reasons, and therefore it would not change the actual nucleus of the atom. It would just remove some energy, and that comes from an atom in an excited nuclear state, an atom with energy to get rid of. It might give out its energy as gamma, and leaving behind the same atom but with a little bit less energy, which we'll look at in the next coming lessons. But we don't actually bother doing that as an actual equation because it's not really overly important. We'll look at something positron emission, electron capture we'll look at when we look at Feynman diagrams, and fission we'll look at in the second half, in the year 13 half of the course. Right, so recapping, we've learned the words nucleon, meaning anything in the nucleus, anything in there. We've learned how to write in isotope form and what the different parts mean. We've learned how to answer the question, what is an isotope? We've learned this term nuclide for all these different types of elements that we might get, the different nucleus arrangements. We've learned specific charge, the charge per unit mass, and we've also recapped how to do the equations for beta and alpha decay, and why the nucleus doesn't rip itself apart because of the strong nuclear force. In our next lesson we'll be looking at photons and the energy of a photon. Thank you for listening.